This is 6-4 inverse trig functions and right triangles put together. So recall that inverse trig functions have a restricted domain. And the reason is because inverse functions have to be one-to-one. So we talked about this in a previous section. So this is just a reminder page. So remember sine, if we restrict the domain of sine, then it does have an inverse. So we restrict this sine function, and we restrict it to the first and fourth quadrants. So in other words, if you think about the sine function when you graph it, it can't be, when you repeat the normal sine function, again, the normal sine function starts at 0 and it does this, and it does this, but to be one-to-one, we have to restrict the domain to be able to do that. So we're literally going to just ignore all that, and we're literally going from here to here and here to here. Okay, so that's why we're restricting it to be able to do that. So you have negative pi over 2, to pi over 2, and then from -1 to 1. And then so we have sine, the inverse of sine, drawing a right triangle in the first quadrant. Then you have sine of theta is y over r, cosine of theta is x over r, and tangent of theta is y over x. So SOHCAHTOA like normal, but just recall that the inverse functions have to be restricted. So we're going to restrict the domain of sine, cosine, and tangent. That way they have inverse functions. All right, so let's look at the domain and the range. So again, this you should kind of already know, because if you think about the sine function, the normal sine function with restricted domain. And again, I just graphed this on the previous page. So we got the domain is from negative pi over 2 to pi over 2, and the range is from -1 to 1. So no, the inverse function, remember when you do inverse functions, you kind of swap the x and the y, the domain and the range. So the domain is actually -1 to 1, and the range is negative pi over 2 to pi over 2. So notice the domain and the ranges of the normal sine function and the inverse sine function. So here we're talking about inverse sine. Okay, so the domain of that and the range of that. And then similarly with the cosine and then the tangent function. So go ahead and pause the video. Make sure you understand the domain and the range relationship between the normal restricted domain and then the inverse functions. All right, so let's talk about finding the exact values of inverse functions of some of the trig functions. So here, finding exact values, so the inverse function of sine to square root of 3 over 2. So what's going to help us out a lot if we go back to the unit circle, and remember the restricted domain of sine is literally from over here. Oops, let me switch it again. Restricted domain is from here to here. And we're doing square root of 3 over 2, and double check, yes, the inverse sine of square root of 3 over 2. And remember, a point is made up of cosine sine. So notice that it would be right there, pi over 3. And then similarly with cosine, inverse cosine of -1/2. So remember the restricted domain of cosine is this top half right here. And we're trying to find inverse cosine of -1/2. So you notice -1/2 for cosine is right here. So this would be 2 pi over 3. And then finally, if we notice the inverse tangent of 1. So if you remember tangent, or tangent function, if we restrict the domain, it's from here to here. And we're doing +1. And remember, tangent is sine over cosine. So we're looking for basically this, because when we put, the y value over the x value, we're going to get +1. So pi over 4 is what I'm looking for. All right, so let's look at approximate values. So this is whenever it says approximate values or round to 4 decimal places, this is where we're going to use our calculator. So go ahead and I'm going to pause the video, or you need to pause the video, and go ahead and calculate the inverse trig functions of each one of these. And again, make sure you're in radian mode for this. And there's the values. I do want to point out the inverse cosine of 2. Remember, the greatest of it, when you graph the cosine function, it only goes up to 1. So there's no way that you can evaluate a function greater than 1 to be able to do that. So this does not exist. All right, so let's actually start using the inverse trig functions of right triangles to find theta, or find the degree. So let's look at this triangle. All right, so since it's based off of theta, we got to find some trig function that involves the opposite and the hypotenuse. Well, that's sine. So what we're going to do is, we know that sine of theta is 6 over 40. Remember, opposite over hypotenuse. That's what sine of theta is. So what we're going to do is to find the actual theta, we're actually going to use a little bit of algebra, taking the inverse sine of both sides. So literally what's taking place is we're doing this. And so we're going to find theta is the inverse sine of 6/40, and then we're just going to use our calculator to get to our answer, and we're going to get 8.6 degrees. Make sure you're in degree mode because we're trying to find the degree of that. And by the way, I just want to let you know that the triangle that I drew may not be drawn to scale because 8.6 degrees is pretty small. So obviously the triangle that I drew is not to scale. But anyway, that's the degree measurement, how much it's opening up. All right, so let's look at another illustration. So the directions are slightly different on this. So it says express theta in terms of d. And so if you look at where theta is, we're not dealing with the hypotenuse. So we're literally going to be doing like the tangent of theta is 2 over d. And since it says express theta, only theta, so we're going to basically be taking the inverse tan. And so that literally crosses each other out. So theta is literally the inverse tan of 2 over d. Notice the directions says express theta in terms of d. So we did what it said. It said there's theta, and we express it in terms of d. So the only variable I have over here is d. All right, so on this problem, it says find all theta between 0 and 180 degrees. So keep in mind that we have 0 to 180 degrees. So we're literally talking from here to here. We want to find all of the theta between 0 and 180 degrees. So I actually wrote the problem wrong, so hold on just for a second. We actually have to have a theta in there. So all right, so find all theta between 0 and 180 degrees. So if we take the inverse sine of both sides, so we're going to end up getting theta is approximately 23.6 degrees. Obviously, make sure you're in degree mode. So 23.6 degrees is right there, and we want to find all theta between 0 and 180 degrees. So another 23.6 degrees. If you literally think of the other 23.6 degree angle over here, the reference angle, and so really we're just going to take 180 degrees and then minus 23.6 to to be able to get to our other one. So 156.4 degrees. So both of these will actually get me the degree angle what I'm talking about. So sine of theta. So this is literally theta, 23.6 degrees, and also 156.4 degrees will actually get you. When you take sine of those, they'll both get you 0.4. Now look at cosine of theta. So if you start finding out cosine, so literally take cosine and inverse. Now, if you remember the inverse trig function is defined already in from here to here, so we can't have a second value. Here you have two different values that will actually get you that theta degree equals 0.4, but here we can only have one degree. It's literally 66.4 degrees. And if you had another one over here, like if you did that, then it would not be 1 to 1. Okay, so here there's only one theta that will actually get you between 0 and 180 degrees. There's only one theta that will actually get you 0.4 to be able to do that. So another way to look at this is if you did do this. If you did, I'm not saying to do this, but if you did this, 66.4 degrees, you're going to get 113 degrees, 113.6 degrees. And if you took cosine of that, that would actually give you negative 0.4. Remember in the second quadrant right here, cosine is actually negative. So there's no way it's going to give you a positive value. Whereas here, back on letter A, sine would give you a positive value in the first quadrant and in the second quadrant. That's why there's two different angles that could give you that. All right, so let's look at another problem. So if I wanted to evaluate cosine of the inverse sine of 3/5. So if we drew a right triangle with theta, and we know that sine is the inverse sine of the inverse sine of 3/5. So that's basically asking me to find out what. So this part right here is asking basically what theta is going to give me sine is 3/5. Well, sine, remember, is opposite over hypotenuse, so this would be 3/5. And of course, we can use the Pythagorean theorem to find out that that's 4. Now so we know then it's going to ask us to find the cosine of that. So the cosine is adjacent over hypotenuse, so this is actually just 4/5. All right, so that's how you would evaluate the function. And let's look at another illustration. So here we have sine of the inverse cosine of x, and notice that I want you to write it as an algebraic expression in x within that restricted x value. So just like the last one, we're going to go ahead and draw a triangle. And notice we're trying to find this part right here. Basically, inverse cosine means I need to find a theta that's going to give me x. Remember, cosine is adjacent over hypotenuse. And we want to basically have this equal x. So just like the last problem, to find this is 3/5, so we made this the opposite over hypotenuse. We made that 3/5. Well, the same thing here. We want to basically make sure that this is x over 1, because that's really what it is. So this is going to be x, and this is going to be 1. And if we use Pythagorean theorem, we're going to find out this side right here is the square root of 1 minus x squared. Then all we need to do is find the sine of that. So sine of theta is basically what we're looking for. So the sine of this, again, is opposite over hypotenuse, which is the square root of 1 minus x squared over 1, which is just that answer right there. So this would be the answer. That's how you would evaluate that. And that's 6.4 inverse trig functions with right triangles.